Hello everyone. In this video we are going to discuss about Cantor's intersection theorem. So let's take a look at what this theorem is telling. The statement of the theorem is let f1, f2, f3 and so on be countable collection of non-empty closed and bounded subsets of R, that means closed and bounded subsets of real number, such that this property is established that F2 is a subset of F1, F3 is a subset of F2 and so on. So basically we are getting a nested kind of intervals here. Then the intersection of all these closed and bounded subsets of R is going to be non-empty. So this is the statement of Cantor's intersection theorem, and let's take a look into the proof of this theorem. So it said that these are countable collection. That means it can be finite collection, it can be infinite collection. So let us break this up into two steps. The first step we'll consider to be a finite collection, and the second one we'll consider it to be an infinite collection. So case 1, let the collection of the sets, collection of the closed and bounded sets be finite. Okay, so this is the first case that we are assuming. So if it is finite, let's take a look diagrammatically what it is saying. So if this property has to be maintained, that means F1 is the largest set, right? So F1 is the largest set, then comes F2 which lies inside F1, or it might be equal to F1 itself. So let's generalize, in a generalized way, let's take that F2 is smaller than F1 and it's lying inside F1. Similarly, F3 is again going to be smaller than F2 and lying inside F2, and so on. This process goes on, right? So we are taking an intersection of all these. Now in this case I have considered, this is case number 1, I have considered that the collection is finite. That means let's say that after a finite number of times I am getting the set Fm, and we are stopping at Fm. I am not going to take any further sets after Fm. That means this series will stop somewhere over here. F1, F2, F3, dot dot dot, ultimately will stop somewhere over here at Fm, right? So obviously you can see from the diagram, if I take the intersection of all these sets, intersection I equals to 1 to m fi, you can see if I take the entire intersection, I'll get just the set which is completely inside the smallest one. That means in this case that's going to be Fm, right? Now it was said that we have to show that the intersection is non-empty. So I've got my intersection to be the set Fm, and it was also told that all these collection of sets, they are all non-empty. So that means this set that I've got, this must be non-empty by the given statement of the theorem, right? So ultimately I've got that intersection of Fi is non-empty, which was my required proof. So case 1 is done. Now we'll come to case 2, where we'll assume that these sets are not finite. It goes on and on infinitely. So let me come over to case 2. So in case 2, I am assuming that my countable collection is infinite. So let the countable collection of the sets be infinite. Now one thing here we are assuming without loss of generality that all these sets are proper subset of the other. Okay, F2 is a proper subset of F1, F3 is a proper subset of F2. If they are not proper subset, then we can make them so. How can we do that? Let me say that F2 is equals to F3. Let's take for example both are equal sets. So if I have F1 over here, I have F2 over here, and this very same set is again my F3 set. This very same is F3 because I've taken F2 equals to F3, and then again I'll have F4. So let's say sometimes when I'm taking this countable collection, some of the sets are becoming equal. So if they become equal, if F2 and F3, if they become equal, we will just take only one of the set and discard the other. Okay, I'll call F3 to be my F2 set. That means I will discard the F3 set, and whatever remaining sets I'll have, I will re-index them, I'll rename them, and I'll call them F1, F2, F3 and so on infinitely. Okay, so basically here, if any one or more sets, 2, 3, 4, 5 number of sets, a block of sets, if they are becoming equal, then we'll take only one set from that block and discard the remaining elements of that block and rename those sets and ultimately call them F1, F2, F3 and so on. So basically here we are assuming that all the sets are a proper subset of the other. So once this has been considered, I can say that Fk minus Fk plus 1, this entire set must be non-empty, because Fk plus 1 is a proper subset of Fk. So if I subtract the two sets, then obviously I'll have some element which belongs to Fk and which does not belong to Fk plus 1. So that means this is going to become non-empty for all k belongs to natural numbers. So this is something we have assumed right at the beginning. Okay. So now one more assumption we'll make, not actually assumption, we'll prove that what I'm claiming is all these sets F1, F2 and so on, all these sets in this infinite collection have infinite number of elements inside them. Okay. Now this is obvious because all the sets are non-empty, each of them is non-empty, and I have infinite number of sets. Now if this is not obvious to you, then let's just take a small example and we can verify this very easily. Let's say that there is some element x1 over here, there is some element x2 over here, just so that we can maintain that Fk minus Fk plus 1 is non-empty. In order to maintain that, I am taking an element x1 which belongs to F1 but does not belong to F2. I am taking the element x2 which belongs to F2 but does not belong to F3 and so on. I am creating the sets. Now let's say that the Fm set contains finite number of elements. Okay, if possible, okay, I'm assuming this, if possible, some set in this enumeration, let's say the Fm set contains finite number of elements. Now this is not possible. Why not possible? Because if I have Fm over here which contains finite number of elements inside it, let's say it contains 5 elements inside it. Okay, just for an example. So if Fm contains 5 elements, then Fm plus 1 will contain, it has to contain at least one element less than Fm because it's going to be a proper subset. So this will contain 4 elements. Then Fm plus 2 will contain 3 elements, at most 3 elements. Fm plus 3 will contain 2 elements. Fm plus 4 will contain 1 element, and Fm plus 5 will become empty set, right? But if it becomes empty, it's going to contradict the fact that all these sets are non-empty. It's going to contradict this fact. So this cannot happen, that any of the set in this infinite collection becomes finite. That is not possible. So that means all the sets in this infinite collection contains infinite number of elements inside them. So in general, I can say that if Fm is finite and contains p number of elements, then this must imply that Fm plus p, after taking the proper subsets p number of times after Fm, it will become empty, which is a contradiction. So that means this implies Fi is infinite set for all I belongs to natural numbers. That means all these sets, all these infinite number of sets, each of them are going to have infinite number of elements inside them. Okay. So once this has been established, let's say I'm taking the elements in this manner. I'm taking x1 which is inside F1 but not inside F2. I'm taking x2 which is inside F2 but not inside F3. in this manner I'm taking elements. So if there are infinite number of elements in this series over here, so that means I'll be getting infinite number of x's in this manner. So let's say I am taking these elements, let s equals to x1 x2 dot dot dot, like this it will go on. And how am I choosing this x? Such that xi belongs to fi minus fi plus 1. You can see x1 belongs to f1, does not belongs to f2. So that means x1 basically belongs to f1 minus f2. If x2 belongs to f2 but does not belongs to f3, that means x2 belongs to f2 minus f3. So in general I can say that xi belongs to fi minus fi plus 1 for all I belongs to natural numbers. So in this manner I have chosen my x elements and I have put those elements inside a set, and I'm calling that set to be the set S. So obviously I can say that here S is an infinite bounded subset of R. Now how could I say that this is bounded? How could I make this conclusion? See, if I just draw the figure, I had my F1 set out here, my F2 set out here, my F3 set out here. So here was my X1, here was my X2, here was my X3, like this it was going on. So you can see from the figure only, all these elements X1, X2, X3 and so on, all of them are lying completely inside F1. None of them are going outside F1. All these elements are inside F1. So if all these elements, if this entire set S, all these elements are lying inside F1, that means S must be a subset of F1. And if S is a subset of F1, it was told to us that all these sets are bounded, right? It was told to us that all these sets are bounded. So if S is a subset of F1 and if F1 itself is bounded, so obviously it implies that S must also be bounded. So that's why I could say that S is infinite as well as bounded, and obviously it's a subset of R. So the moment I could tell this, now I can apply Bolzano-Weierstrass theorem. Bolzano-Weierstrass theorem. What was the statement of Bolzano-Weierstrass theorem? Bolzano-Weierstrass theorem told us that every infinite bounded subset of R has at least one limit point, right? If you are unaware of this theorem, you can check it in my YouTube channel. I have created a theorem related to Bolzano-Weierstrass theorem. I'll put the link in the description box. You can look into that. So if I apply this theorem over here, I can claim that this set S must have a limit point, right? So now I'm bringing that into the picture. So from Bolzano-Weierstrass theorem, I can say that this implies S contains, or not S contains, I must say that S has a limit point X. Now this limit point might not belong to the set itself. Okay, so I'll say that X belongs to R, because limit point might belong to the set, might not belong to the set. You're not sure about that. So to be specific, we'll say that X is some real number, X belongs to some real number such that it is a limit point of the set S. Okay. Now the moment we have established the existence of a limit point of this S set, now we are going to claim that this X element is going to be the limit point of all these sets. Okay, now we are going to establish that. We are going to establish that X is going to be the limit point of F1, F2, F3 and so on, all the countable number of infinite sets. It's going to be a limit point of all of them. So let's see how we can do that. So we assert that X must be a limit point of F1, F2, F3 and so on. Okay. So now I'm going to prove this assertion. Okay, let's come back to here. As we said that X is a limit point of the set S, Now from the definition of limit point, what can I say? That there exists some neighborhood of x, some epsilon neighborhood of x, such that the neighborhood intersection the set itself is infinite, or it contains infinite number of elements. Okay. So this comes directly from the definition of limit point, that there exists some epsilon neighborhood of x such that its intersection with that particular set is infinite. Now I'll box this and I'll call this 1 because I'll just require this later on. So the moment I write 1, remember this line. Okay, now I'll come back over here. So let me do this by a contradiction process. Let me assume that let if possible x is not a limit point of some set fm which comes in the iteration. Okay. So if this is not a limit point, x is not a limit point of fm, if it was a limit point, then its neighborhood with the fm set would be infinite. Now if it is not a limit point, that means the epsilon neighborhood of x intersection the fm set, this must contain finite number of elements, because if it was a limit point, then it would contain infinite number of elements. So if it is not a limit point, it must be containing a finite number of elements. Now what is going to be the problem for this thing that we have got just now? Again, I'll go back to the picture. This was my f1, this was my f2, and like this, suppose this is my fm. I had my x1 over here, I had my x2 over here, and just inside my fm set I'll have the element xm, and so on. The process will go on. So you can see the element xm, then the next element we would have got, that would have been xm plus 1, and so on, starting from xm, then xm plus 1, xm plus 2, and so on till infinitely it will go on. All these elements you can see are lying completely inside the set fm, right? So here I have an observation that the set xm, xm plus 1, dot dot dot, this entire set is a subset of fm, right? We are getting that directly from this diagram. So if this set is a subset of fm, then I can obviously say that from this line that I've got, in x epsilon intersection the set xm, xm plus 1, and so on, this is also going to be finite set, right? Because if intersection of some neighborhood with the fm set, if that is finite, and now if this fm contains these elements as well as many other elements, so I'm taking a subset of fm. If I take a subset of fm, so intersection with this neighborhood is still going to be finite, because basically I have reduced my fm set. If the initial thing was finite, then after reduction of that set, it's obviously going to remain finite. Now if I add a few finite number of elements over here, it's still going to remain finite, it's not going to become infinite. So I am adding a few finite number of elements over here. What are those elements? Let's say I'm adding the finite number of elements to be x1, x2, dot dot dot, xm minus 1. These are the finite number of elements I have added, and these elements were already there, which is xm, xm plus 1, and so on, right? So if this intersection is finite, if I add a few finite elements in that intersection, it's still going to remain finite. So this thing is still finite set. Now the thing that we can see over here, this set that I have formed, this is basically my capital S set. My capital S set was x1, x2, dot dot dot, infinitely it was going on. So I have got my capital S set over here. So basically I have got n x epsilon intersection S is finite set. Now is this possible? See, this is not possible. Why? Because S, this x element was the limit point of S. So if x was the limit point of S, I already told you in the number 1 numbering which I made, that this intersection contains infinite number of elements because X is a limit point of S. So this is not possible, right? Because this intersection was already infinite, which I have claimed in number 1. So that means this implies this is a contradiction. So why did we arrive at this contradiction? We arrived at this contradiction because we had assumed that X is not a limit point of Fm. We had assumed this, that's why we reached at this contradiction. That means the assertion that I had made that X must be a limit point of all these sets, so that means this assertion is correct, right? So now again I'll come back to my assertion and I'll continue from here. So that means I have got that this implies X is a limit point of f1, f2 dot 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 infinitely. Now another important thing which we haven't yet used over here, it was said that all these sets are countable collection of non-empty closed subset of R. So we have not yet used the fact that they are all closed. So now I'm going to use the fact that all these sets are closed. Now what is the benefit of being closed? If X is a limit point of any closed set, then X must be belonging to that set. That's a property of a closed set. If some set is closed, then the limit point of that set cannot lie outside the set. It has to be inside the set. So I can say that since Fi are closed, this implies X belongs to Fi for all I belongs to natural numbers, right? So the fact that they are all closed makes this conclusion that this X belongs to all the sets F1, F2 up till infinity. So if X belongs to all the sets, then what will be my intersection? My intersection must contain the element X because X belongs to all the sets. So this is non-empty. Why non-empty? Since X belongs to this set, it is non-empty since X belongs to this intersection. Right? Now I cannot say that the intersection contains the element only X and no other element. Maybe there are many more limit points other than X. Maybe there are many more number of limit points, so this intersection might contain many more number of points, but that's not our lookout. Our lookout is we have to show the intersection is non-empty. So we have got at least one element which belongs to this intersection, and that makes this intersection non-empty, and hence our theorem has been proved. Okay, thank you everyone for watching.